Okay. Assalamualaikum and good morning. I think we can continue our class today. Okay, so last week we discussed about the principle of capacitive transducer. So today we continue. Uh, we will continue with inductive transducer. Where first, um, the principle of inductive transducer is based on the same principle as a transformer. Okay, so we can first consider uh, two set of coil. Okay, like we have in this picture at the bottom. Okay, so these two coil is basically sharing the same core. Okay, I mean uh, the core supposed to be an iron core. Okay, so it's look like a bobbin. The primary is wound on the top of the part of the core place, and then the secondary coil is wound on the bottom part of the iron core place. Uh, since this transducer work same principle as a transformer. So uh, it works at AC or alternate current. Okay. So we in drive or give the uh, primary power source with the AC signal. Good. Okay, this is sine wave signal EX with the amplitude of EX. Okay. Then the, so when we give the primary the primary and AC signal, so it will generate a uh, magnetic flux. Okay, so if the uh, secondary coil is a secondary coil is aligned like this, okay, means that at the same at a certain axis, but uh, apart away, it means that it put this there's a distance between the primary and secondary. So the flux, uh, magnetic flux, there will be no magnetic flux linkage. Okay, linkage from the primary to the secondary. Okay, so in this first condition, on as you can see from the figure on the bottom left, so E out, okay, will be 0. Okay, the magnitude or the amplitude of E out will be 0 volt because there is no magnetic flux linkage. Okay, so the magnetic flux only surround is only generated around the primary core, and then due to the distance, the air gap, okay, between the secondary and the primary, there there, there is no flux linkage. Okay, but when we put an iron core, okay, an iron core is a, okay, iron core. This is the ferromagnetic material. Okay, so the flux that is generated around the primary core will be linked. Okay, basically, the okay the flux, okay, the flux, okay, will be linked to the secondary coil. Okay, so in this case, okay, so if we have a, okay, let's say the primary input, okay, this is our primary input, E, EX, input, okay, and due to the flux linkage, so there will be EMF generated, okay, between on the secondary coil, okay, but okay, we will notice phase difference, okay, phase difference, and also E out is proportional to EX, okay, depend on the number of windings. So basically the proportional or the ratio depend on the number of winding of the secondary to the uh, to the primary, okay. So basically E out will be proportional to the ratio of the secondary to the primary, E, E. So, but in negative due to the phase shift, okay. So so the, so this is due to the mutual inductance, okay. We change and resulting in a voltage change in the secondary coil, okay, in terms of the magnitude, okay, value, and also the phase shift. So in when the iron core, let's say this is a null position, okay, or the origin position, where there will be a maximum linkage, okay, so the output uh, at the secondary will be, the magnitude will be maximum, okay. But as we move the iron core, okay, whether up or down, we will notice change the output voltage on the secondary coil. So that movement, okay, so that reflect the displacement, okay, displacement. So basically the displacement and an object is attached, or an object is attached to the iron core, and then due to the displacement, it will the output of the secondary coil will be proportional to the displacement. Okay, so uh, that is the basic principle of a transformer. Okay, but we modify the transformer to construct what it called as a LVDT, or what or linear variable differential transformer. Okay, so in a linear variable differential transformer, so we have three sets of winding. Okay, three sets of winding line in the same axis. Okay, line in the same axis. Okay, place apart. So an LVDT has three sets of winding. Okay, this is the physical construction of an LVDT. So in the middle we have the primary core. Okay, and then we have another two identical set of secondary winding or secondary coil. Okay, so we have a primary and then we have a secondary. Okay, so the primary will provide the uh, main signal, okay, EX. Okay. So and then in the middle, okay, of the winding there is a core. Okay, then this core will move up and down, okay, representing the displacement. Okay, we can say, okay, up, okay, we can say this direction, and down we can say this direction down. Okay, that is representing this placement. Um, so in a LVDT, okay, the two secondary coil are wound in opposite direction, such of that if the core move to either direction, the induced voltage on one of the secondary coil increase and decreases in the other. So meaning to say, in the secondary we have two set of winding, but normally we don't use it separately, but rather we use the winding together. Okay, so as you can see, okay, this is okay, winding of uh, the first secondary coil. Okay, E1, E1 plus minus. Okay, connect to the main circuit, positive. Whereas the negative, okay, the negative terminal of first secondary is connected to the uh, negative. Okay, negative uh, terminal of the secondary coil. Okay, the number two secondary coil. Okay, secondary coil 2. Okay, and then this positive is connected. Positive terminal of the secondary is connected to the main circuit here. Okay, so the total output from the secondary coil, okay, E is E1 minus E2. E1 minus E2. Okay, so so we will look into the output in detail later. Uh, Basically, when the core is located at the center, okay, or what is called as null position, NULL, the null position, or X or displacement equivalent to 0. Okay, displacement is equivalent to 0. So the amount of flux linkage, okay, on the first and secondary winding will be equivalent. Okay, will be equivalent. So the total, uh, so the mutual inductance will be the same, will be equal at E1 and E2. So therefore, the magnitude of E1 will be equivalent to E2. So E1 minus E2, the output will be 0. Okay, the output will be 0. So that is when the core is at null position. This is not at null. Null means that the core exactly at the center. Okay. Now this is the we represent the output. Okay, of the primary and secondary voltage. This is show the primary and secondary voltages at null position. Okay, so we can draw here. Okay, so we have our primary, and then we have our secondary. Oh, sorry. Okay, so this is our secondary. So this is E1 plus minus, and this is E2. Okay. So this is our input EX. Okay, let's say EX. Okay, and in the middle is our core. Okay, let's say our core is at null position where it is at the center, where X is equivalent to 0. Okay, so the input, okay, I can see the input as a okay, so the input as the amplitude of EX. Okay, EX. Okay, and you can see when the core, okay, is at the center, so the flux linkage are equal, and so the mutual induction are due to the equivalent of mutual inductance in the uh, first and secondary. Okay, so you can see here, okay, the output E1, okay, E1, okay, E1 is out of there's a phase difference between the, okay, this is the primary, this is the primary input. Okay, so this is the first secondary. Okay, and this is the secondary. Okay, so the E1 is equivalent to E2, okay, in terms of the amplitude. Okay, the amplitude is equivalent. Okay, E1, E2, the amplitude is equivalent, but and also E1 and E2 are in phase. But if you look at E1 and E2, it is out of phase. Okay? So there's a phase difference. Okay? We call it theta. Okay. So because it is a work as depend on the mutual inductance, so there will be a phase difference. But if you can see when the core is at null position or origin position, where x is equivalent to 0, so E1 is equivalent to E2. Okay? So E1, in this case, E1 is equivalent to E2. So E1 is equivalent to E2, the outputs at the first and secondary, uh, the second secondary. So therefore, okay, the total outputs, okay, at the secondary here, E out, E out is equivalent to E1 minus E2 will be 0 volt. Okay, so this is the output when the uh, core is at null position. Okay, so we look at this uh, another slide. Okay, so this is the okay base diagram of the uh, LVDT. Okay, so we have a main primary giving input, okay, 3 to 15 volts, okay, and amplitude, and the frequency operation around 50 hertz to 20 kilohertz. Okay, and then we have the core, okay, the core that move that measure the or connected to an object that measure the displacement, okay, whether the moving up or down, so or represented as x, positive or negative. And this is the secondary winding. Okay, the second we have the okay, so this is our first E1 here. This is our E2, and we know that E out is equivalent to E1 minus E2. Okay, so this we look at the okay. If we look at um, the several the output secondary voltage at different position. So when the core is at null, so so the output E out is equivalent to 0. Okay? But if the core is above the null or is moving upward x, okay, bigger than 0, moving above the null, so you can see the output, okay, as shown as the figure in the top. But when the core move below the null or x is less than 0, okay, so you see the output is identical to the output when the core is above the null, but it is 180-degree out of phase. Okay? So if we if we look at the output the output the output in terms of the uh, waveform. But if we take the amplitude, okay, we take the amplitude, okay, and then we take the amplitude. Uh, so this is the absolute value of the output voltage or the amplitude for different position. So if the core is at the middle, okay, at the middle, so we know that the uh, output of the first secondary and the secondary will be equivalent. So E out will be E1 minus E2 will be equivalent to 0. So this is when the null position. Okay. So if the okay core move above the null position, above the null position or x is bigger than 0, so we can see the amplitude, okay, E out is increasing. So the output will be proportional. Okay, proportional, and at some point, okay, you see this point where the output will be diminish or going out or reduce, and then at this point it will be gone. That is because the core is moving out from the core. Okay, moving out from the core. If we can push it too far above the null position, so the core will be out of the core, and then uh, there will be no flux linkage. Okay. Same thing we observe, okay, when the core is moving uh, below the null position. Okay, below the null position, okay, we get the same relationship where the output or the amplitude will be uh, proportionally will be increased. Okay, the output or the absolute value will be increased when the core is moved below the null position. But and then at some point, same thing. What happened? The output will diminish and gone. Okay, because the core have totally moved out from the core. Okay, uh, so so in this case, uh, in this case, we don't we it is in some case it is very important, okay, to know the exact or, movement or direction of the displacement. So from this information, okay, from this information, uh, it is not very clear to for us to know whether the core is moving upward or downward. We can only know this from our observation, but if we only depend on the output, okay, the output, let's say we get the output at this, okay, this level, okay, okay, the magnitude, just the magnitude or the output, we don't actually know whether the core is moving upward or downward. So uh, to solve that problem, uh, we use a signal conditioning circuit. Okay, the signal conditioning circuit, uh, which is called as the phase sensitive electronic circuits. Okay, okay. So the phase sensitive uh, circuit is basically comprised of a bridge. Okay, as shown here. Okay, so this bridge, okay, is constructed at the first secondary and also at the second secondary. Okay, so when when the core is at the center, so E out will be equivalent to 0. Okay, but when the core is moved above, okay, above the basically when it move above the null position, okay, or we move x more to 0, bigger than 0, so what we can see, okay, E out, okay, E out, okay, due to this phase sensitive circuit, okay, E out will be like this. Okay, I think I will draw that again. Okay, when it move above the null position, okay, So the E out, okay, will be like this. Okay, E out. Okay. But when the core is moved below the null position, or meaning above the null position, and if they move below the null position, okay, or x is then when we move downwards. Okay. So here, okay, E out from the phase sensitive circuit, okay, give like this, okay, where E out is negative. So we have a full wave, okay, with negative amplitude. Okay. So in this case, okay, if we take the magnitude, okay, absolute value, okay, and the total output of the phase shifting circuit will look like this. Okay, so this is null position, okay, null position. So this is when the core move to, above the null position, or you can say positive x. And this is when the core move to below the null position, or negative x. Okay, negative x, so we move downwards. So at the magnitude here, you can see uh, is a linear, okay, relationship, okay, where E out is equivalent to K X. Okay, K is the sensitivity. Sensitivity. Okay, so sensitivity, okay, we can calculate from by measuring the slope, okay, of the linear line here. Okay, so from this phase sensitive circuit, we can immediately understand, okay, when if the output is negative, that that meaning that the core is moving below the null position, okay, the null position. So we can exactly know where is the position of the core. Okay, and when the the E out is positive, okay, so we know that it is the core has moved above the null position. So this is the principle of a phase sensitive circuit, which is a signal conditioning circuit for the LVDT. So and then we have a counterpart, okay, device of a LVDT. So LV called as RVDT. So LVDT is used to measure linear, whereas for LVDT, okay, is used to measure rotation. Okay. So the similar transducer, it is a similar transducer to LVDT in terms of the principle. This is a inductive transducer. It depends on the mutual inductance between the primary and secondary windings. Okay, so the rotary variable differential transformer, or RVDT, is for measuring angular displacement. Okay, so instead of linear, so in this case it is used to measure rotation. Okay, rotation. Okay, in many applications, such for example to measure the position of the motor winding, okay, to measure the for it is a very old. I mean, it has been used since World War I, where World War II, where this wine transducer is used on the tank, where they use it to measure to estimate the position or the angle of a turret of a tank. Okay. Okay, so now we move on to strain. Okay, strain is another completely different transducer, and strain, okay, is a device or transducer basically to measure deformation or strain. Strain is a mechanical or deformation is or commonly called as mechanical deformation, okay, or mechanical strain. Okay. Uh, so uh, so basically, how we measure is basically is by estimating the change of length divided by the total length of the object or the device. Okay. So that is called as the strain. So this is basically a mechanical quantity. Okay, so this device, okay, is called as strain gauge. Okay, the name is strain gauge. Okay, it's basically made of an insulating flexible metallic foil. Okay, so there's a metallic foil, okay, covered in insulator, a thin plastic. Okay, and it's basically a conductor, okay, a wire, a very thin wire. Okay, a very thin wire. Okay, package or covered or put into a flexible material like film, film, a plastic film. Okay, and then this device, okay, uh, as a terminal. So this terminal we connect to a circuit. Okay, this terminal we connect to a circuit, and this strain gauge we attach. Okay, attach the strain gauge on the surface of the object, okay, where we want to measure the mechanical strain or the deformation. Okay, so the principle is that as the object is deformed, okay, so it causes the foil to deform. Okay, the coil is basically, okay, a piece of conductor, okay, where it has a electrical characteristic or the resistance. Okay, so basically when the foil is stretched, okay, the wire is stretched, and then causing the change, okay, change on the coil, okay, change of the resistance of the coil, delta R, okay, delta R, okay. So the R or the resistance of the coil is equivalent to rho L over E, rho L over E. Proportional rho is the constant of the material uh, the coil, okay, the coil, and L is the total length of uh, the coil. A is the cross section of the coil. So when when the coil is deformed, okay, the coil is deformed, it causes the either causing the change of the total length and also change on the surface area. So due to the change of the uh, variables, okay, so it cause we can detect the change of the electrical resistance. Okay, and then this electrical change or the resistance change delta R. Okay, usually we measure a Wilson bridge. Okay, we measure using a Wilson bridge because uh, uh, this is a passive transducer where the output is not self-generating. Okay, meaning to say it does not generate its own EMF. So we need to use a signal conditioning circuit to relate between the input with the output voltage. Okay, so in this case, the input is strain or the mechanical deformation. Okay, and then the final output is voltage. So to have that final output voltage, we have to apply a resistance bridge. Okay, okay, okay. So the resistance, like I explained, okay, the resistance of the uh, strain gauge wire or the coil is given by this formula R equivalent to rho L over A. So rho is the constant. It depends on the type of conductor material. So if the conductor material is let's say cuprum, so they will be a specific value. L is the total length of the conductor. Okay, total length of the conductor or the strain gauge wire. Okay, and A is the cross section area of the conductor in square meter. Okay, cross section area of the wire. Yes. So R will be proportional to the L total length and also inverse proportional to the area. Okay. So in this figure, as you can see, okay, so the strain gauge, okay, is uh, attached, okay, glued on the surface of metal steel. Okay. So do you want to or maybe this metal bar is used as a connector that support a very heavy load. Okay, so support a very load. So then we want to see, okay, how uh, the this piece of rod, okay, handle the load. Okay, the load it support. Okay, so we want to by measuring the total amount of strain. Okay, the strain, okay, which we measure from the output. Okay, the output here. Okay, okay, see this is uh, the sample of application of strain gauge. Okay, sample application of strain gauge. Okay, where we have a specimen. Okay, specimen where we want to uh, analyze, okay, the behavior of the test specimen. So we want to know how the specimen how it reacts to force. Okay, and also we want to estimate at when at what point this specimen start to fail when we apply uh, different amount of force. Okay, so we want to see when it is start to fail. fail. Okay. So in this example, we use two set of strain gauge. One set of strain gauge is placed on the top of the specimen, okay, and then the second strain gauge is placed on the bottom of the specimen. Okay, and then we use a Wheatstone bridge. Okay, we use a Wheatstone bridge. So at zero force, okay, zero force, when zero force is applied, so we assume that the bridge is balanced where R1, R2 are equivalent, and then there is another two fixed resistor. So we can estimate the outputs here will be equivalent to 0. Okay. So when we apply a force, okay, depending on the direction of the force, let's say the force is pushing the specimen downwards. Okay, so when the specimen is pushing downwards, okay, meaning to say that the resistance of R1 will increase and R2 will decrease. Okay, so causing the bridge to be unbalanced. Okay, so when the bridge unbalanced, the output is okay. We can be measured across the Houston bridge, but when the force is uh, applied on the different direction, so uh, so we can see the R1 strain, the first strain gauge resistance will decrease and the second will be increased, and then the polarity of the resistance bridge output, okay, will be uh, will be will be changed or will be inverse. Okay, positive, negative. Okay, when we apply the force, okay, at different direction, we apply force from down from the bottom to up at the tip of the split test specimen. Okay, so a few things that you need to know about strain gauge. There are a few variables that you need to know. The first variable is called as the uh, gauge factor or key. Okay, gauge factor is sometimes it's written as K, sometimes it's written as GF, gain factor. So, K is also the uh, uh, common variable name for the gauge factor, and the gauge factor K is actually the ratio of the relative change of the resistance to the relative change of the relative change of the uh, total length, okay, or the mechanical strength. Okay. So the relative change of the resistance is written as delta R over R, okay. And the mechanical strain or the relative change of the total length, okay, is written as delta L over L. Okay. So this is gauge factor. Okay. Sometimes the strain, okay. So this is the relative change of the resistance. Okay, this is the relative change. So this is the relative change of total length or some or mechanical strain. Mechanical strain. Okay, so mechanical strain, and sometimes and then this mechanical strain is okay. Mechanical strain is written as G. Okay, G. So this is equivalent to G. So then we have this formula. Okay, so the strain gauge, or so the gauge factor is equivalent to the relative change of the resistance delta R over R divide to the strain or G, G or mechanical strain, okay, G. Next, we need to know the uh, stress. Okay, stress is stress, mechanical stress S equivalent to force divided by the area. Okay, okay the stress is in kilogram per square meter or sometimes in Newton per square meter. So the force is can be in kilogram or Newton. Okay. Area is in meter square. It is in meter square. So stress, the stress, same equation as pressure. P F A same, same. Okay. Then another equation you need to know is the constant proportionality between stress and strain for a linear stress curve is known as the modulus of elasticity of the material, E, okay, or Young's modulus. Okay, E is the ratio of strain to the gauge factor. Okay, E is the strain to the gauge factor G. Okay, G. Okay. G, where do we get the G? G you can get from the gauge factor, okay, equivalent to delta R over R, okay, over G. So G we, then can be obtained from the gauge factor. So G has no unit. The Young modulus, okay, Young modulus sometimes is written as EM, small l. So the unit is in kilogram per square meter or in Newton per square meter. Newton per square meter. Okay, or negative to the power of 2. And the strain in kilogram per square meter or in uh, Newton per square meter. Okay. So let's look at this example. Okay, the strain gauge. So a strain gauge having a gauge factor of 2. So gauge factor or K is equivalent to 2. Okay. So that is the first key variable. Is mounted on the rectangular steel bar with EM K 20 times to the power of 6 kilonewton per newton. EM is the modulus. Okay, modulus, Young's modulus E. Okay, EM. In this case, EM is Young modulus E equivalent to 200 times 10 to the power of 6 kilonewton per meter square. Okay. The bar is 3 centimeter wide, 3 centimeter wide and 1 centimeter high. Okay. So wide and high This is so 3 centimeter, 1 centimeter. Okay. And subjected to a tensile force of 30 kilonewton. So F is 30 kilonewton. Okay, kilonewton. Determine the resistance change. Okay, if the resistance order was 120 ohm in absence of the actual load when the force, so basically when force equivalent to 0 Newton, 0 Newton, so R is 120 ohm. Okay, so the question is to find what is the uh, resistance change, what is delta R. Okay, so we have a few information there. So first, we need to measure the strain. The strain S is equivalent to F over A. Okay. So this is in kilonewton per meter square. So, so we have the force is 30 kilonewton. Okay, divided by the uh, area in meter square. So meter square 1 time to the power of negative 2 multiply with the width 3 times 10 to the power of negative 2. So we have our strain to be 1 times 10 to the power of 5 kilonewton per meter square. So now we know our strain. Okay. So how to next we need to calculate the uh, gauge factor. Okay, the gauge factor from the modulus Young. The gauge factor. So we know that EM is equal to S of over G. No. We need to now. The next is to find the mechanical strain. So mechanical strain. Okay. Find the mechanical strain from the modulus Young. So our modulus Young is 2 here, and then we know our strain is here. So we calculate that our G. Okay, so S strain okay, here. Sorry, stress. Okay, our stress S is from here. Okay, stress. So and this modulus Young, and then we need to know the mechanical strain. So the mechanical strain is 5 times 10 to the power of negative 4. Okay, negative 4. Okay. So this is dimensionless. Okay, or meter over meter. So now we have our G. Okay, so we have our G. After we have our G, so we can calculate the resistance change. Okay, the resistance change. Okay. So we know that gauge factor, okay, K is equivalent delta R over R divided by G. Okay. G is the mechanical strain. Okay. So we know our K Okay, from this to then we know our R here. R is 120 ohm and G is here. Okay, 5 times 10 to the power of negative 4. So then we can calculate delta R. So if you work it out, so our delta R is supposed to be 0.120. Okay, okay, so that is from this example. So the other application of strain gauge is to measure the mechanical strain on an aircraft. So the strain gauge is attached on some point. Okay, many maybe can even okay, put in many points. Okay, where you need to know how the wing, the airplane's wing, behave or react to the force when it is mid-flight. Okay? And also it is used to measure the strain of construction like buildings, okay, uh, or like bridge, like roads. Okay, we place that under the bridge, for example, based on the pillars of the building, and then we want to see how it react to the earthquake. Okay, like skyscraper, a very high skyscraper like KLCC or some or any similar building. Uh, you observe it very carefully or you observe it in detail. These skyscraper they are actually wobbling, I mean moving a bit, okay, to the left and right, especially when the wind is blowing very strong. Okay, so actually, strain gauge is used to measure how building behave, or it can be used as a sensor to detect when the construction start to fail. If um, they can estimate when the problem start to appear. Okay, this is example when it is used under the bridge. Okay, bridge have a okay actually is a constructed to be supported by wires. Okay, wires. So basically, they really depend on uh, the strength of the wire to support the road. Okay, uh, so the strain gauge is and then the bridge okay, will have a lot of vehicles moving on the surface, especially like heavy vehicle, okay, like big trailer or lorries. Okay, so you need to see how the bridge, okay, condition, okay, how do they behave over the time, and then you want to see any change. Okay, so if there is a significant change over the time, okay, so they can take quick action. Okay, so let's say if the stress is start to increase, whereas the bridge cannot recover, okay, after it was applied a certain force, so they need to take action like repairs, and they need to identify the part where it has a problem. Okay, and also, okay, strain gauge is used and applied on the rail, the train rails. Okay, so train rail to check, okay, the lateral or the vertical uh, part of the rails. Okay, so they need to check whether it's still good, still can withstand the heavy load of the train or the locomotive. Okay, so this is an example. Another example, a strain gauge is used to detect the strain on building due to wind or earthquake, and the circuit connection is shown in Figure 1. Okay, calculate the value of the strain gauge at balance condition, and second, what is the change in resistance strain with the gauge factor. Okay, change in resistance. Okay, delta R. What is the delta R? What is delta R? Okay, where the gauge factor is 5 when it's subjected to a strain. Okay, strain G. So G, G mechanical strain of 4 times 10 to the power of 6. Okay, so let's uh, first we need to know what is the default value of the strain gauge when it's no stress. So this is a Wilson bridge. Okay, Wilson bridge R1 over R2 will be equivalent to R2 over Rg or the strain gauge resistance. Okay, okay. So Rg will be equivalent to R2 over R1 multiply with R3. R2 is 4.5. K divide with R1 is 2K multiply with R3 is 3K. So Rg, the default value is supposed to be I get 6.75. That is what I get. So this is the default value of the strain gauge when there is no force or strain subjected on the strain gauge. Okay, so we need to know to calculate delta R. So we know that gauge factor here, gauge factor is equivalent to delta R over R divided by the strain, okay, G. Okay. G strain is actually delta L over L, but in this case it doesn't mention the change of length. Okay, so we can work out the value of delta R. So delta R over R is equivalent to GF multiplied with G. Okay, GF multiplied with G. Okay, so delta R will be equivalent to Rg. In this case is Rg. Let this consistent now. Okay. Rg multiply with Gf multiply with G. Okay, so we have that Rg is 6.75. Okay, and our strain is 4 times 10 to the power of 6. But I think the it's not to the power of 6. Sorry, to the power of -6. Let's see. Yeah, to the power of negative 6. So negative 6. Yeah, negative 6. Okay. And then multiply with G. G is gauge. So the GF, the gauge factor is 5. Okay. So G is okay. So the change of resistance supposed to be 135 multiplied with 10 to the power of negative 6. Okay. Or 0.136 milliohm. Okay. This is what I got. Okay, this. Okay. Now, before I stop today's class, I need to touch a bit on the topic of this is the last subtopic, but I need to touch this, and then I need you to have a read of this chapter before we start or we continue next week, because this one it requires some reading. Okay, and then you need to understand some standard. Okay, and this is pretty much standard where you need to remember and then to memorize. Okay. This subject explains the about the piping and instrumentation diagram, or P&ID. Okay, P&ID is very important in the industry. This is a figure of a typical chemical plant. It consists of the combination of uh, many sub plants or sub processes. Okay, so basically they have separate sub processes to combine together to do a process like a refinery. Okay, for example, like what we have in Pasir Gudang, in the factory where they some chemical plant they process uh, chemical to produce fertilizer, for example. So they involve a lot of sub processes, and these sub processes have a lot of equipment, and then they have many transducer, and it require description. Okay, so the chemical process diagram, basically it is a drawing, engineering drawing that defines the chemical process step in proper sequence pictorially. So means that the chemical process they have many pictures they put in the sequence. Okay, and then the sequence means that in an order which uh, which process or come first in the total process. And the chemical process diagram shows us the elaborate representation of the equipment and also the sequence, and also explain the performance of the plant. Okay, so you as a engineer need to know the chemical process diagram, okay, because of you want to fulfill the requirement, like for example the design, okay, the cost estimation, okay, the procurement, okay, fabrication, operation, maintenance, and also for management in the record, and most importantly for safety. So during the plant design, so you need to also during the plant design, so you need the chemical process diagram to understand the process requirement, and also it is important during the operation. So you need to verify the operating performance as stated in the design. Uh, and also it can be used to provide or to formulate to come out to come for you is very important for you to come out with the standard of safe operating procedure. Okay, and then also it is important for training or induction. So you want to tell other people when, okay, let's say someone who have moved on, okay, or the actual person who has already set up the process, and then somebody want to take over. So then so the new person or the new engineer, okay, you can take over by looking at the chemical process diagram. Okay? So it is a very important document in the to understand the process during the operation and also during the maintenance, and also to maintain the high safety level of the plant or the process. Okay, so there are the many types of chemical process diagram. Okay, for example, there are block flow diagram. There are flow diagram, process flow sheet, or PFDs, piping and instrumentation diagram, P&ID, and utility flow diagram, UFD. Okay, but in this subchapter, we will only look at the P&ID, whereas the others we may, or if you are a chemical engineer, you may cover that other areas. Okay, so we concerned about P&ID because uh, we will function as a electrical engineer or instrumentation engineer. So a P&ID is is a diagram in the process industry which shows the piping of the process together with the installed equipment and instrumentation. Okay. So there is the body which provide the standard. Okay. For example, the Institute of Instrumentation and Control UK. Okay, so there are other association like International Society of Automation or ISA. So they are working together. Basically, they are working together to provide the standard for P&ID. So P&D is basically according to the to the definition of Institute of Instrumentation and Control UK. Is a diagram which shows the interconnection of piping, process equipment, and instrumentation used to control the process. Okay. So, in other words, it actually represents a schematic of the all equipment, piping, and process instrumentation. Okay. So, as a engineer, okay, so we use P&ID to understand the process and how the instrumentation is uh, wired. Okay, how the instrumentation is wired. We say so we need so it give us a clear understanding on how all the equipment are connected together and how they in whether they are independent or interdependent in some process. Okay. So P&ID is used during most plant activities such as normal operating condition, okay, startup and shutdown. regular maintenance and emergency. Okay, so P&ID is always being referred. Okay, like for example, before uh, you start the system, okay, during the design, before you commence. Okay, and also it is used during the maintenance, okay, where you want to see troubleshoot or you want to repair or replace something. Okay, you want to identify, let's say the system identify an error at a certain spot, but you need to know where exactly is the equipment or the location, so we can use the P&ID to locate, so to assist us to locate the actual location of the equipment. And also in emergency situation, if there is a breakdown, so we can use the P&ID, okay, to bypass or to stop this, to safely stop the system. Okay, so we cannot simply immediately stop the system, but if we have a PID or we have familiar with the P&ID diagram, we know which point we can safely turn off. Okay, but in the chemical process, you cannot simply turn off at any point, especially when it is involved high pressure or heavily extreme heat, okay, or very strong flow or very high pressure flow. So it is very important to refer to the P&ID diagram. So the P&D can be divided into three parts: the equipment specification, okay, equipment specification, instrument specification, and also piping specification. Okay, basically the equipment specification, for example, what is the purpose of the variable controlled by the equipment, okay? Okay, and what is the uh, equipment function, okay? And also instrument, okay, there are different between equipment and instrument. Okay? Equipment usually the electrical controller, okay, but instrument usually can be a valve, okay, can be a fitting, okay, okay. So this tell us the specification. Okay, and now the piping specification tell us whether the piping, okay, whether it is transferring liquid or is transferring gas, pressurized gas, and so on. We will, so that is what the P&ID is divided to. So basically, we can from the P&ID we can know the material flow, the material type, liquid, whether it is liquid or gas, okay, or multi-phase. Multi-phase is the combination of liquid and gas. Okay, piping, okay, piping between the various section. Okay, let's say for example the main pipe go to the junction and so on. Okay, major pieces of mechanical equipment, okay, equipment like valve, okay, you have your valve, okay, valve and direction of process flow, whether it shows whether it's go one direction, unidirection or unidirection. Okay. Field mounted equipment. So some equipment instrument. So some instrument is put in the field. Okay, put in the field, and then it has an indicator. Okay, but some equipment is put inside the control room or put in a control box. Okay, and then electrical equipment. Okay, there's a difference between the electrical connection between controller to a device or from device to control device to other device. Okay, like valve to the controller, and also we want to see the communication link between the instrument and equipment. For example, some instrument, uh, so it communicate with other device pneumatically or using the gas pressure. Okay. So the P&ID is not to show the process information, okay, the exact dimension or the dimension size. So that's not the purpose of the P&ID. Piping detail means that how long or how far the piping, and also it is not, the purpose not to show the control logic. Okay, it just show the information above. Okay, so uh, the P&ID show the equipment symbol, piping symbol, and instrument symbol. Okay, the equipment symbol, it will show you the equipment layout where the location, and also the identification and the numbering. So there will be a lot of equipment. Okay, and also the identification. There will be a lot of different uh, function of equipment like pressure control, temperature control, okay, so pH control. So we need to identify, and also even in pressure control, there will be many controller. So we need to have a different numbering. The piping layout is used to show how the layout of the piping. So how the equipment and instrument interconnected. Okay. And instrument also similar. So equipment, the instrument is like uh, equipment is a control device. So instrument is the device being controlled. Okay, like valve, okay, for example, okay, and heating element. Okay. Also, it can be like mixer or other thing like motor. Equipment is the basically a control device. Okay, so we look into the some example later. Okay, so equipment uh, shows us the shape like, okay, like sphere, tank, column, pumps. Okay, also the orientation, whether the equipment is horizontal, vertical, or slope. Okay, and then the size. Okay, and then the status. Okay, for example, this is a tank, vertical tank. Okay, uh, we have vertical pump or horizontal pump, or vertical pump with different size. Okay, different size. This one is different size. It shows us the layout, and also symbol. Okay, this is very important. Uh, the identification process. Uh, we are using a tag system. A tag system. Usually, this is the basic tag system where we have three lines, one, two, three. But in our example, we will only use two lines. Okay, two lines. So, for example, the first line shows the equipment, the type of equipment, okay, whether it is a storage tank, pump, filter, cooling tower, and so on. The second tag shows us the number. So there will be like similar equipment like tank. There are many tanks, but we give it a different numbering. Okay. And then the third one is the tag root alphabetic. This is also if you have a subsystem, then you have many other uh, other other similar equipment. That, for example, in the same tank, there are two pumps. Okay, two pumps. So this third one is give let tell us the versions or the other sets. But in our example, we only use the two line of text. Okay, okay, so I want to you to later to read about this graph. Okay, this is a standard identification letter given by ISA S511. This is standard. ISA is just instrument, the International Society of Automation. So ISAS 5.1 is a instrumentation symbol and identification standard. It's a standard. So here, like the first tag here, okay. In the first tag, we can have 1 to 4 character or 1 to 4 numbers or letters. So normally, for example, the first letter shows us the measured or the initiating variable. For example, A is for analysis. Okay, that's the function. F flow rate or the variable. Okay, another like P pressure, T temperature, and V vibration. Okay. And then the second letter comes is the modifier. Okay, give us the uh, modifying condition. Okay, for example, uh, differential. Okay, differential. Like for example, pressure differential. Pressure differential means that the equipment function based on the differential. It measure the output. The variable is measured based on the differential pressure of the input and of coming from the input. Okay. Okay, so the other letter, like for example, uh, indicator I, means this I indicator. That indicator means that function is to indicate. Okay, or we use C is for control. Okay, okay, C and so on. And then you can see. Uh, this is the in details. Okay, the other letter in details from A to A to Z. Okay. So for example, we have this our equipment, okay, equipment. Uh, so and then we have our tag, two lines of text, okay, top and bottom, two lines of text. Okay, so the tag is inside the circle, and there is a line divided between the tag. So we will explain to that later. Okay, so this is the tag. For example, the first letter X, right? Okay, measured variable. Okay, can be P, L, F, or T. Okay. The second succeeding is the function or the function of the component, or to modify the meaning of the first letter. Okay. It can be the second letter can be I, indicator, recorder, controller, or transmitter. So we will into that. And the bottom one is the series number of the equipment. Okay. For example, okay, here, so we have a simple example. Okay, so let's start from here. Here we have a temperature sensing bulb. So this is sensor, temperature sensor. Okay, connected to this TT. Okay, TT. TT. The first is T means the variable temperature. T is transmitter. Transmitter means that it converts the output to current. Okay, current. So that's the transmitter. Okay, current 4 to 20 milliamp level. Okay, so the output from the temperature, okay, could be voltage. Okay, and then this transmitter convert the output voltage of the temperature sensor into proportional current signal. Okay, 4 to 20 milliamp. So usually in the industry we convert the signal into current, or because current, okay, is less susceptible to noise. Okay, then it is connected to another equipment. Okay, with the tech TRC. Okay, so and then with the number 206, so you see all these equipment has the same number, meaning that they are functioning, or they are grouped in the sub process of 206. Okay, 206 in your P&ID diagram. So this one is TRC, temperature recording controller. Temperature, okay, is the variable, and then this is the first function is to record. Okay, to record means that we can have a check the output, okay, over the time. So we can download the temperature, okay, recorded at a certain infinite period of time. Okay, and then the second function is controller. So controller means that this equipment is used to set, okay, to set an output, or an action when the temperature, for example, has reached, okay, a certain level. For example, if the temperature, okay, is below than 100 degrees Celsius, okay, let's say when below than 100 degrees Celsius, so this will send, okay, a signal to the valve. Okay, valve, this is valve FCV, flow control valve. Okay, valve, this control valve. So maybe, so this flow control valve, okay, is, okay, the steam. Let's say steam is coming in. Okay, so when the temperature is less than 106 degrees Celsius, so this controller will send a signal to the valve to open. Steam will come in and then will heat up the liquid inside the tank. Okay, okay. So these three are in connected. How it actually connected? Okay, and interdependent. But here we have one device. Okay, TI, temperature indicator. Okay, TI. TI, so this is sensor. They measure the temperature, okay, of the tank, but it has no connection to the other equipment. So this one is only display. Okay, just display the output. Okay, probably on just somewhere outside the tank. Yeah, just outside the tank. So it is used for like operator to check, immediately check the current output of the tank, and also it is used, it this one is used to verify the output, okay, the output, okay, coming out from the temperature transmitter. Okay, so that is one example. So I think what I want you to do now is to read, okay, this example. Okay, next week, inshallah, we will discuss in details of the other content of this the last subtopic. Okay, I think for that is all for today. Okay, basically today, and inshallah we will meet again next week.